So what we're looking today at is errors and bounds. And basically it's all to do with rounding numbers. So for example, we're all used to rounding numbers to a certain number of significant figures or decimal places or to the nearest 10 or something like that. But we're almost working backwards here, and there's a question here: what are the upper and lower bounds and the error interval of a value that has been rounded to 7 to the nearest whole number? Now, imagine we've got a number line. Here's our 7. We've got 6 over here, and then 8 over here. Okay, it's not too complicated so far. What we want to do is think, okay, what numbers, if I'm rounding the nearest whole number, what numbers get rounded to 7? And nice and easy. If that was 6.8, for example, that would get rounded to 7, wouldn't it? If we're rounding to the nearest whole number. Or if we had 7.3, that would get rounded down, wouldn't it, to 7? And in fact, anything between 6.5 will get rounded up to 7. Anything between 6.5 and 7 will get rounded to 7. Yeah. Anything less than 6.5 will get rounded to 6. And it's the same up at the top end here. So if we think about 7.5, anything 7.5 and above gets rounded to 8. But anything below 7.5, so even if I took something like 7.499999, if we were rounding that to the nearest whole number, we would round it to 7. Okay. And so what we've got is this basically this interval anywhere between 6.5 and 7.5. So we include 6.5, but we don't include 7.5. And this is what we call our error interval, or the value could be anywhere between 6. And this bottom number is what we call the lower bound. It's the lowest value. Oh goodness, what's just happened there? Sorry. Thank you, Ben. So we've got our screen back, thankfully. This bottom value that would get rounded up to 7, we call the lower bound. And the top value, so in this case 7.5, we call, funny enough, the upper bound. But the upper bound isn't actually included in this. So if we wanted to talk about this interval, this whole area between 6.5 and 7.5, we often write it as an inequality. And what we'll say is, okay, our value x, or whatever it is we're measuring, is anywhere between 6.5, and it can be equal or greater than 6.5, but it's strictly less than 7.5. And this is then the error interval. Okay, so we can write this in two ways. We can say, what's the biggest value that could be rounded down to 7? And actually we just say the upper bound of this is 7.5. What's the lowest value possible? Well, the lowest value is the lower bound, which is 6.5. And if we want to write that as an interval, then we can write it as an inequality, where the bottom one is always included and the top one isn't. And these values here, we simply put the lower bound is less than equal to something which is strictly less than the upper bound. Okay, and that's all that we're doing. We're finding what's the biggest and lowest values that could fit into this. Now, you'll see that if we were measuring this to the nearest whole number. And actually our nearest whole number was 7. But if you look at this, we've gone half a unit below 7 and half above 7. And this is a very quick way of working out the upper and lower bounds. If you work out what you're measuring to the nearest, so the nearest whole number, then you can take half of that and go half of it below and half of it above. So here I'm measuring to the nearest whole number, the nearest 1. So half of 1 is a half, so let's go half below 7 and a half above 7. And those are our upper and lower bounds then. So just going to write that in. So if we measure a value to the nearest unit, then the upper bound is half that unit above our approximation. Oops. And the lower limit, or the lower bound, sometimes you'll hear it called the lower limit, but the lower bound is half a unit. Oops. Half a unit less. And we'll see how that plays out in the next slide. So basically here, we're measuring to the nearest 1. So half of 1 is a half. So we're saying, okay, 7 is our approximation. Let's go half below and half above. That's our lower bound and our upper bound. So let's look at this here. So we've got 800 to the nearest 100. We're measuring to the nearest, the units are hundreds. So what we're going to do is we're going to add 50 and we're going to subtract 50. Half of 100 is 50. And so the upper bound in this case is 850 and the lower bound is 750. We go 50 more than 800 and 50 less than 800. And if we want then to write that as an inequality, we'll say that, okay, 750 is less than or equal to our value, which is strictly less than 850. In this next one, look, we're measuring to the nearest 1 decimal place. Now, a unit in the first decimal place is 0.1. So half of that is 0.05. So we're going to add 0.05 and take away 0.05 from 4.3. Oops. So our upper bound is equal to 4.3 plus 0.05, which is 4.35. And our lower bound is 4.3 minus that 0.05, which is 4.25. And again, if we wanted to write it as an interval, we'd simply say 4.25 is less than or equal to our value x, which is strictly less than 4.35. Actually, we'd round 4.35 up to 4.4, but because we write it like this with the inequality, we can call this our upper bound. 17 to the nearest whole number. Well, the nearest whole number is to the nearest 1. So we're going to add and subtract half of that, so 0.5. So our upper bound is 17.5. Add a half. Our lower bound is 17 minus a half, which is 16.5. And again, write it as an inequality. 16.5 less than or equal to x, which is less than 17.5. We're measuring to 2 significant figures, which is slightly different now. When I look at this, I've got 1 is my first significant figure. The 3 is my second significant figure. Now that's in the tens column. Okay, yeah. Hundreds, units, sorry, units, hundreds, tens. Rubbish, sorry. Units, tens, hundreds. So we're measuring this, although it's the 2 significant figures, our answer is to the nearest 10. So here we're going to add and subtract half of that. We're going to add and subtract 5. And so our upper bound is 130 plus 5. And our lower bound is 130 minus 5. And again, we can write that as an inequality. Okay. Folks, any questions on that slide just to start with? Oh goodness, that seems to have stopped again, hasn't it? Okay, don't worry so much. I'm going to upload this later anyway, so you'll get all the PDF notes of it and also the video of it, okay? But let's move to the last slide then. And hopefully, I'm just going to stop sharing and start it again because it seems to have... okay, hopefully this will work a bit better. There we go. Okay. So the last two here, and this is just to show slight difference, just need to be slightly careful. Here, first one we're measuring to the one decimal place. And the decimal place is tenths, so 0.1 is a unit in the decimal place, first decimal place. So what we're going to do then is we're going to add and subtract half of that, 0.05. And so our upper bound here is 11.4 plus that, which is 11.45, and our lower bound is 11.4 minus that, which is 11.35. And again, we can write it as an inequality if we want. The lower bound is included in this. I'm just going to say t. Could be any letter in the middle there. It doesn't have to be x. You know, if you're talking about time, t would be a much better letter to use. If you're talking about mass, m might be a good letter to use. But in this second one, which looks very, very similar, it's actually measured to 2 decimal places. And the second decimal place then, we're talking about the hundredths column. So we're measuring to the nearest hundredth, 0.01. So half of that, we're going to add on and subtract half of that, which is 0.005. It's 5 thousandths. And so the upper bound here is 11.405. The lower bound, just be slightly careful with this, 11.40 take away 5. And so, albeit those look very, very similar, we get slightly different answers for that, depending on how many decimal places we're rounding to. Now these are important. Oh, my screen has just stopped again. These are important because we can use calculations involving these upper and lower bounds, so it's very important that we can work them out, and we will be looking at these then on Friday.